Dear students, today we will discuss a tutorial on analysis of COP of absorption refrigeration cycle and test procedure and performance analysis of a PVT collector. Let us consider the theoretical COP of an absorption cycle first. Let me draw the flow diagram of a vapor absorption refrigeration plant. Okay. So, we will draw this plant first, then it will be generator. Okay. So, solar collector will generate heat, okay, and it will go here, again it will come back to the solar collectors. Okay. There are many collectors, and then we will have a condenser here. Okay. So, we have to supply some kind of fluid to cool the refrigerant. So, we have to remove the heat, maybe QC, and we have to add heat from the solar collector, which is nothing but QG, because this is a generator. Okay. And we will have expansion valve, and then we will have evaporator. Okay. Then from evaporator it will go to what is called absorber. Okay. So, this is absorber, okay, and we have to circulate fluid to extract the heat of the solution. Okay. So, this QA has to be removed, and here this QE, that much of energy, which is nothing but absorption of heat from the atmosphere. Okay. And then we will have heat exchanger here, okay, and maybe we will have pump here. So, strong solution will have to move up, and we have a valve here, and it will go down. Okay. So, I will write what are the components. This is WP is the pump work, okay, and this is also known as aqua pump, and we will have a strong solution here, strong solution, and we will consider aqua ammonia solution. So, ammonia vapor will be here, which is at higher pressure, and this is condenser, already known to us. This is condenser, and here cooling water will be circulated, cooling water to condense the vapor, and then this is expansion valve, expansion valve, okay, where pressure will be reduced from say 10 atmosphere to very low pressure. Okay. So, here it is a QE, okay, and this is evaporator, and here brine solution or sodium chloride is introduced. So, maybe sodium chloride in water. Okay. This is evaporator. Okay. Heat exchanger, right. This is ammonia vapor, it is a low pressure. Okay. So, we have already discussed the working of vapor absorption refrigeration cycle in the earlier classes, where we have learned that the absorption refrigeration system is a heat operated unit which uses a refrigerant that is alternatively absorbed and liberated from the absorbent. Okay. So, here in this case refrigerant is ammonia when you talk about aqua ammonia refrigeration system, and water is absorbent, right. So, we will start with this generator. So, this is generator. So, what happens, heat of this solar collector which takes the heat, and then this ammonia will be vaporized at high pressure, and that has to be condensed in a condenser by circulating cooling water, and then this liquid refrigerant pass through this expansion valve where pressure is reduced significantly, and then we have this evaporator where space need to be cooled. Okay. Here sodium chloride in water, that solution is used, okay, and heat is taking from the atmosphere. Okay. And then this low concentration of ammonia which introduced in the absorber, where water actually comes down and mixes with this ammonia vapor, and then here what happens is heat of the solution has to be carried away because this has to be maintained at constant temperature. Then what happens, it will become very strong solution. Okay. So, ammonia concentration will be more, and that has to be pumped through this heat exchanger to this generator. Okay. So, it works in a loop, right. So, as you know, this boiling point of ammonia is less than that of the water, the ammonia vapor is given off from the aqua ammonia solution at high pressure, right, here, and this weak solution returns to the absorber, okay, through this pressure reducing valve. Okay. So, this is important, right. So, now what we will do, we will do the analysis for calculation of theoretical COP of an absorption system, right. So, let us draw the figure first. So, if we consider a source here, source which is at temperature T1, okay. Already we know the source is giving heat to the generator. So, we also know what term represents amount of heat which is given to the generator, which is Qg. Okay. So, it goes to generator. So, I will write this is generator, and then it goes to condenser, then we have absorber, I will write absorber, and we have evaporator. And here we need to maintain this region, okay. This region need to be cool, right. And from condenser and absorber we take out heat Qc, and then we have Qa. Okay. So, if we make this is a sink, okay, sink at T2, and this is the region we can take Tr is the temperature need to be maintained for the refrigeration purpose, right. So, here this dotted portion is nothing but absorption unit. Okay. So, this is absorption unit, absorption unit, right. So, here what you can see, Qg is the amount of heat we have given to this generator, and Qc is the amount of heat which is carried away, and Q is the amount of heat we have taken from the atmosphere, and then Qa is the amount of heat which is given off, okay? That is heat of the solution, right, because we need to maintain at constant temperature this absorber. Okay. So, source is T1 and then region temperature is Tr and sink is Qc plus Qa. We are considering something like this, right. Now, let us develop the expression by taking the help of first law of thermodynamics and second law of thermodynamics. What will be the maximum coefficient of performance of an vapor absorption refrigeration cycle, right. By the first law of thermodynamics, we know it is energy balance Qg. So, amount of heat we have given, then Qe we are taking from the atmosphere, and then Qc plus Qa we are discharging. Okay. So, let this equation be 1, and by second law of thermodynamics, we have delta S entropy of the source plus the entropy of the sink plus delta S or entropy of the region which has to be greater than or equal to 0. Okay. So, entropy has to be greater than or equal to 0. So, locally entropy may decrease or increase, okay, but no resultant entropy should always increase. That is the second law of thermodynamics in terms of entropy. Now, when we are taking heat from a source, then what happens? Then entropy will decrease, right, because randomness of the molecule will decrease. Something like, we can give an analogy, like if we consider a silent library and a busy street. So, when we sneeze in a silent library, what will happen? Then there will be lot of destruction, there will be lot of molecular disorderness, right, because of that there will be rise in entropy. If we sneeze or same level of sneeze if we make in a very busy street, then the rise of entropy will be not much. Okay. Again, when we take heat from a high temperature source, then entropy will be negative, okay, entropy will reduce, right. So, that is how source is at high temperature. Okay. So, the amount of heat we are taking is Qg at what temperature is at T1 plus sink is getting the heat. Okay. So, there will be rise in entropy, because when we are dumping heat, then what will happen? There will be lot of chaotic motion, right, like we are sneezing in a silent library, right. So, under that condition we can see Qc plus Qa is like T2. Okay. So, sink temperature may be at T2, and then here again we are taking heat from the atmosphere, then this will be negative, right, at Tr. So, this will be something like this. So, we can name this equation as 2. Now, using equation 1 in equation 2 we have minus Qg by Q1 plus Qc plus Qa is nothing but Qg plus Qe divided by T2, right, minus Qe divided by Tr, which has to be greater than or equal to 0, right. So, if we simplify it, then it will be something like T1 minus T2 divided by T1 into T2 to Qg. Okay. So, this part we can couple, this part and this part we can couple. Okay. So, if we do, then our expression will be something like Tr minus T2 divided by T2 Tr Q E greater than or equal to 0, right. So, again if we simplify it, T2 minus Tr divided by T2 Tr, which is less than or equal to how much it will be, T1 minus T2 T1 multiplied by T2, which is Qg, right. So, again we can simplify. So, what will happen? It will be Qe. So, I missed one here, it will be Qe. Okay. So, this Qe divided by Qg, which is less than or equal to T1 minus T2 divided by T2 minus Tr, okay, and this has to be multiplied by Tr by T1, right. So, if we are interested about COP, coefficient of performance, that is maximum or maximum coefficient of performance, which is equal to, we can write T1 minus T2 divided by T2 minus Tr multiplied by, we have Tr by T1, right. So, again we can simplify it something like Tr divided by T2 minus Tr multiplied by, we have T1 minus T2 divided by T1. Okay. So, what is this now? These two parameters. So, what does this indicate? This is something like ideal coefficient of performance of a refrigerator. So, that is working between T2 and Tr. Okay. And what is this? This is the ideal thermal efficiency. This is the ideal thermal efficiency of a heat engine. I will let HE, which indicate heat engine, working between T1 and T2, right. So, what we have evaluated? So, when we are interested about COP of a vapor absorption refrigeration system, which is nothing but multiplication of COP of a refrigerator working between T2 and Tr and ideal thermal efficiency of an heat engine working between T1 and T2, right. So, that gives the maximum theoretical efficiency, right. So, now what we will do, we will take one example and try to see what will be the maximum COP of a vapor absorption refrigeration cycle, right. So, our problem goes something like an aqua ammonia absorption refrigeration system. Heat is supplied to the generator from an array of solar collector at 120 degrees C. The temperature to be maintained in the refrigerator is minus 10 degree C and the ambient temperature is 30 degree Celsius. Estimate the maximum COP of the refrigerator. Okay. So, we need to solve this problem now. So, here what is T1? T1 is nothing but source temperature, right, which is 120 degrees C, then we have to convert to Kelvin, right. So, 120 plus 273, which is nothing but 393, okay, that is in Kelvin. So, what is T2 here? T2 is 30 degrees C, right, 30 degrees C, which is the sink temperature, right. So, 30 plus 273, which is nothing but 303 Kelvin, right. And then TR is given. So, we need to maintain the region temperature at minus 10 degree C. Okay. So, minus 10 plus 273 will be 263 Kelvin, right. So, if we know these three temperatures, then we can calculate the maximum COP, right. So, we know the expression for maximum COP, which is nothing but T1 minus T2 divided by T2 minus TR multiplied by TR by T1, right. So, if we substitute these temperature values, so T1 is 393 minus T2 is 303, then here T2 is 303 and TR is 263. Again we know here TR is 263, T1 is 393, right, 393. So, if we do the calculation, then it is found to be 1.5, right. So, maximum COP of a vapor absorption refrigeration system is found to be 1.5, okay, which is very less if we compare with vapor compression refrigeration system, right. Now, if we are interested about actual COP, this is the maximum what we have calculated now. So, if we say the actual COP is 40% of the maximum COP, okay. So, if the actual COP is 40% of the maximum COP, then what will happen? COP, if we write actual, then it will be 1.5 multiplied by 0.4, which will be about 0.6. Okay. So, actual COP will be about 0.6, right. Again, if we consider say refrigeration load is say about 20 tons. Okay. So, if we say Q E is something like 20 tons, right? Then how much heat is required? So, solar collector is here, solar collector, I will write here C, then we have to transfer some kind of heat, right, which is QZ. So, if evaporator load is about 20 TR, ton of refrigeration, then how much heat is required? If we need to calculate, then how we will proceed, right? So, if we consider QE is equal to 20 tons, so that means 1 TR is how much in kilojoule per hour? It will be 20 multiplied by 14000 kilojoule per hour, right. So, we can convert it to kilowatt if we divide the expression by 3600. So, 20 multiplied by 14000 divided by 3600. Okay. Then what we will get, the value of QE is equal to about 77.77 kilowatt. Okay. So, that way we can calculate what is QE, and then if we need to calculate QZ, how to calculate? We know actual COP is nothing but QE divided by QZ, right. So, this QZ will be something like QE by COP actual. Okay. So, if we substitute this value, QE is 77.77 kilowatt and COP is 0.6, then what we will get? It is about 129.629 kilowatt. So, that much of energy is required to provide refrigeration effect of 20 TR. Okay. So, that is how we can do the calculation about the heat required to run the refrigeration system. Okay. Now, let us discuss the performance analysis of a solar PVT collector. Okay. It includes test procedure, performance parameters, and then example, right. So, here what you have seen, one experimental setup, schematic and one photograph, right. So, here this is the PVT collector need to be tested. Okay. So, we have a test bed. So, you can fix the unit at a particular tilt and we make all the arrangements of measurement. Okay. So, you can see the actual picture, how we have a mounting structure and all the measurement facilities. Okay. So, what are the instruments required? For measurement of solar radiation, we need a pyranometer. Okay. So, this is the pyranometer. Okay. So, pyranometer is here. So, pyranometer will give us the global radiation, and also we need to measure fluid inlet temperature, fluid outlet temperature, PVT surface temperature, then absorber temperature, then ambient temperature. So, for measurement of these temperatures, we have a data acquisition system, okay, which is a very sophisticated data acquisition system. So, we need the sensors and that has to be connected. So, this is something like this. So, we can get the data in every second, what is the variation, and of course, we need a PV analyzer which actually tells about the IV characteristics at particular time. Okay. So, from that we can calculate what is the maximum voltage, what is the maximum current. Okay. Also, we have used one temperature gun, okay, to know the cell temperature, right. So, here solar radiation is falling here, and then this is the collector we need to be tested, and we have to circulate known quantities of fluid. So, mass flow rate is constant, okay, and then fluid inlet temperature is constant, and then outlet temperature can be measured, okay, and we need minimum solar insolation of 700 watt per meter square. For these parameters we followed standards, right. So, let us see how we can move to what is called indoor experiments. The one what I have shown, that is a real time experiments, and what I am showing here is the test facility which is developed inside the laboratory. Okay. So, this figure shows the schematic and this figure shows the photograph, right. So, here we will have anemometer to see the wind velocities, because wind velocity also need to be controlled while performing the experiments, and we have light source. We have given the sufficient light like simulation of our sun, and we will have pyranometer to see the radiation intensity, okay. And we have this fluid tank with heater. So, we need to regulate the inlet fluid temperature, that is why we need this regulation tank, and then mass flow rate is fixed, okay. So, under that condition we have measured all the variables like what is the Vm, what is Im, what is surface temperature of the cell, what is ambient temperature, what is fluid inlet temperature, what is fluid outlet temperature, right. So, photograph can also be seen here. So, this is an indoor test facility, okay. So, we have followed the following test procedure to derive thermal efficiency curve, like minimum requirement specified in EN 12975-2 is to generate performance, and we have performed the experiments when solar radiation is more than 700 watt per meter square, and to compare the thermal efficiency of different collectors, the flow rate should be kept at the same value, right, and initial temperature we controlled in the range of 25 to 45 degrees C. So, we have performance parameters which need to be calculated, like electrical efficiency. So, how do we calculate electrical efficiency? Once we know Vm Im for a particular set of experiments, and we know the collector area and then amount of solar radiation which is falling on the collector, then from that we can calculate the electrical efficiency. And for thermal efficiency we need to calculate the useful heat gain and then amount of solar radiation received by the collector, okay. So, this mCp dt is nothing but TFO minus TFI, okay. So, this is nothing but useful heat gain, right, and this is the amount of radiation received by the collector. Then from that we can calculate what is the thermal efficiency. So, once we know both electrical and thermal efficiency, then we just add it, right, which will give you energy efficiency. And fourthly, what we are interested about, Exergy efficiency of a PVT collector. So, which can be expressed by Exergy output to the Exergy input. So, if we need to find out the Exergy input, then we need to follow this expression. So, which is a function of this ambient temperature, sun temperature, then we will have amount of solar radiation received and then collector area, okay. So, once we know these parameters, then from that we can calculate what is Exergy input. And when we talk about Exergy output, there are two components, that is electrical component and thermal component. For electrical component, we can calculate this Exergy output by multiplying Vm and Im, and for thermal Exergy output we can get from this expression, right. So, QE is the useful heat gain which is already known to us in this calculation, and TA is known and TFO is known, then from that we can calculate what is Exergy output for thermal, okay. So, we will combine this and then we divide the expression with Exergy input, then what we will get is a Exergy efficiency of a PVT collector. right. So, let us take one example, like calculate the average electrical, thermal, energy and exergy efficiency from the given set of data. Consider mass flow rate as 0.015 kg per second, and also plot various parameters against the time of the day. Okay. So, this is data what we have generated in our experiments, right. So, this is the timing and solar radiation is given here. So, this is global radiation and we have used pyranometer, and then ambient temperature is recorded and fluid outlet temperature is also recorded and fluid inlet temperature is here, and then output power is known from the IV tracer. Okay. So, normally what we do when we test a solar collector, we normally perform the experiments during these hours 11:30 to 13 hours or 1 p.m. Okay, because during that time we will get maximum exposure to the sun, right. So, our primary data will be this for performance analysis, but also we can see what happens if we perform the experiments from 9 to about 3:30 p.m. right. And we need to consider the surface temperature of the sun is 6000 Kelvin and area of the collector is about 0.67 meter square. Okay. So, what I will do first, I will do one calculation and I will show you, then we will use one spreadsheet to calculate all the parameters for a single day starting from 9 a.m. to 15:30 hours. Okay. So, first let us calculate what is electrical efficiency for 11:30 a.m. Okay. So, here if we take the value of Pm, which is multiplication of Vm and Im. So, these are the maximum voltage and maximum current. So, here it is 71.2, right, and AC is given to us is 0.67 and Z value, which is solar radiation, is about 870. Okay. So, if we calculate it, it is found to be about 12.21 percentage. Okay. So, the next case what we will do, we will calculate the thermal efficiency. Okay. So, this is at 11:30 a.m. Okay. So, mass flow rate is given as 0.015 multiplied by CP value is 4.18 into 10 cube multiplied by, we will have 39 is the TFO and 32.3 is the TFI, okay, inlet fluid temperature, and area is 0.67 and Z is 870. Okay. So, once we do the calculation, then what we will get is the value of thermal efficiency, which is nothing but 72.06%. Okay. So, I am just showing one calculation, okay, then we can use the spreadsheet, as there is no point of doing all the calculations here. So, when we talk about energy efficiency, which is nothing but 1 plus 2. So, here we are adding, but sometimes we cannot add it because quality of both the form of energy is different. So, it will be something like 84.27%. Okay. And the next what we will calculate is about exergy efficiency of a PVD collector. Okay. So, now we will calculate one by one. So, let us first calculate Exergy output. Okay. So, which is nothing but Vm into Im. Okay. So, this value is PM. Okay, PM is already given, which is nothing but 71.2 plus we will have QU. So, we will write QU here, and then we will have 1 minus TA is 33.6 plus 273, and then we will have 39 plus 273. Okay. So, here we will write QU is equal to M Cp then delta T. So, if we substitute the values of mass flow rate, which is 0.015 multiplied by 4.18 into 10 to the power of 3 multiplied by 39 minus 32.3, then this is found to be about 420.09. Okay. So, here you can see the unit. Okay. So, your M is in kg. So, here joule per kg per degree Kelvin. Okay. This is Kelvin. So, this is coming right, and this is mass flow rate. Okay. So, joule per second is watt. So, this will be in watt. So, here if we substitute the values, then it is found to be about 78.47 watt. Okay. So, Exergy output. So, this is known now. Okay. So, now what we need to calculate is Exergy in. Okay. So, we can use this expression. So, straight away we can substitute the values here. So, AC is 0.67, G is 870, then we have 1 minus 4 by 3, then TA is 33.6 plus 273 divided by 6000. Okay. Plus 1 by 3 multiplied by TA is again 33.6 plus 273 divided by 6000. Okay. So, if we do the calculation, then Exergy input is found to be about 543.19 watt. Okay. So, this is Exergy input, right. So, now what we will do, we will substitute this value and this value in this equation. Okay. So, Exergy efficiency will be, Exergy output is 78.47 and this input is 543.19. Okay. So, this is found to be 14.44 percentage. So, we need to multiply 100 to get percentage. Okay. So, this is the Exergy efficiency, right. So, once we know these values of temperatures, okay, and then solar insolation and then maximum power, then from that we can calculate all those efficiencies, right. Now, what we will do, we will go to the spreadsheet and see how we can generate the plot and do the calculation. So, all the values are calculated here for 9 am, 9:30, 10, 10:30 till 15:30, and you can see the efficiency, electrical efficiency, thermal efficiency, energy efficiency and Exergy efficiency, right. So, if we take out these values from here and we can make a separate table and we can generate this kind of plot, right. So, maybe we can see the variation of efficiency with respect to the solar radiation, then what happens, and then again we can see the variation of all the efficiencies at different times. Okay. So, with increase in time what happens, there is increase in efficiency till mid of the day, then it is decreasing. Okay. All the plots showing the similar pattern, but electrical efficiency is lower, okay, compared to thermal efficiency, right. So, by utilizing this PVT technology, we can harvest both the energy, electrical energy as well as thermal energy. So, that is why it is shown. So, otherwise this energy, heat energy would have been wastage. Okay. So, we could not tap this energy. So, by attaching something at the beneath of the PV collector, and then we are circulating fluid. So, of course, there are some configurations just beneath of the PV. So, water is circulated in those tubes. Normally, we have used some kind of tubes, and from that actually we can harvest this thermal energy, and this thermal energy can be applied for many of the applications. Okay. So, once we generate this plot, then we can take from here and we can use it here, because this problem is asking about the plot. Okay. So, we can have this kind of plots finally, and these are the results what we got from the analysis, and this electrical average efficiency is 11.67 throughout the day. Average thermal efficiency is about 60%, average energy efficiency about 71%, and average exergy efficiency is about 13.32%. Okay. So, this way we can do the analysis and investigate the performance of a PVT collector. So, in summary, what we have done, we have investigated the COP of absorption refrigeration cycle, and theoretical COP also we have calculated, and we have discussed the test procedure of a PVT collector, and also we have studied the performance of a PVT collector with an example. So, I hope you have enjoyed this video. Thank you very much.